Okay, so welcome to this tutorial on linear regression. We're going to start off here with some very basic simple linear regression where we're just going to fit a line to some data, just a single straight line. And it's really good to get our heads around this because this basic simple linear regression actually forms the basis for, in terms of my day-to-day work that I do, about 95% of the statistical analyses that I do are revolve around linear modeling to some extent or other. So if we can get our head around this, we should have a good foundation for many of the rest of the types of analyses and models that we do. So we'll see here we're working on, we're working on this in this folder here. We're working on L15 linear regression, the folder there in the R lectures from GitHub. Where are we there? And I'm working with this markdown file here. We'll come on to this one later on in a subsequent podcast, this markdown file here, and we've built and knitted it to this. So we can take a look here. It's a good time as well, I think, in this course to just go through a little R markdown embellishment. So you'll see here in the text component, not the R chunk, in the text component, we use these dollar signs here, and that lets us specify maths. It lets us specify mathematical relationships and formulate equations. And if we use either side of a single use of a dollar sign, we get over here then or actually it's better to look here. So between these single line here, we've specified, written out an equation. Single dollar signs render, you'll see if I hover over it, it renders it as a mathematical formula here like this, but that renders it what's called inline in the text. So here it is over here in the HTML. It's inline, so it's just an equation pasted into the sentence where it appears in the raw markdown here. But then if we use these double ones here, so we use double quotations here, we get a preview on the R markdown here. If you've got RStudio up to date, you'll get a preview shown here of an equation typed out longhand here, and that then renders on its own line, sitting on its own line, floating here in the HTML. So that way we can start introducing some maths. There's lots of different ways of formatting the content of that. You'll see here, for example, underscore denotes a subscript. / beta denotes the lowercase letter beta. Capital B there will give us an uppercase beta. So /beta, so \beta underscore 0, it renders as lowercase beta, subscript is 0. I'm not going to go through that. That's LaTeX style formatting. You can Google LaTeX math equations, or you can Google Markdown math equations, and you'll get a load of examples if you want to start rendering your own code and functions there. So we'll plow on with this. So linear regression, in school, I don't know if you all learned it, but in school I learned it as the equation of a line is y equals m times x plus c, where m is the slope, c is the y-axial intercept, y is the y-axis, and x is the data on the x-axis, and so that describes the relationship of a straight line. In statistics, though, we tend to write it out slightly differently. So in statistics, we'll render it like this. We'll say y, some response variable, some data that we have, is equal to our b naught, beta naught, plus beta 1 times xi plus epsilon I. So yi, so the ith, however, we've got 10 data points, we'd have I equals 1 to 10. So our y data here, each data point is equal to some number, b naught. All the yi's have the same b naught. All the yi's have the same b1, so it's b1 times xi plus epsilon I. And the epsilon I is important because this would be the equation of a perfect straight line here, but we know in statistics nothing is perfect. Data is noisy, data is messy. We'll never explain all our data with a simple straight line. And so we add this epsilon on, which is error or uncertainty, or how much it deviates from that line, is essentially what that is. So that's the equation of the line. So each data point, each yi, to calculate that yi, to calculate the estimate of that, get to that yi, essentially this is a mapping. This maps a number in x onto a number in y. So to calculate yi, we take the corresponding x value. So if it's the second value in y, we take the second value in x, we multiply it by beta 1, we add on beta naught, and that gets us pretty close. So that'll get us onto a straight line, but we need to actually get to our data point yi, we need to add or subtract a tiny amount of error, hopefully a tiny amount of error here, and that's what this epsilon I is. So that's how we'd normally write out our equation of a straight line. So it's a straight line with some error and noise. We can calculate, you can sort of, in a statistical sense, there's different ways of thinking about this. You can think about it like that works just fine. The other sort of way of doing it is to sort of break this up into two parts. So what we do is we'll define the overall expected value of yi. So the expected value of yi is just this bit here. It's the beta naught plus b1 times xi. So the mu I, the mean expected value of yi, is beta naught, the intercept, plus beta 1 times xi. So that's the expected value on its own. So that's where we'd expect to get to. And then separately, we can write the error. The error then is written as the expectation of the error is that it's normally distributed. So it's a normal distribution with mean 0. So we'd expect most of our data points to fall either side of our line. So we've got a mean of 0 and a standard deviation there of sigma. I'm actually going to rewrite that because I've rewritten that down below here as a variance. So you can specify a normal distribution as either having a mean and a variance, or a mean and a standard deviation, or a mean and a precision, which is 1 over the variance. I'm going to stick with variances because it's a bit more how I'm sort of thinking about it these days. So the variances here, they're also a bit easier to work with mathematically. Variances, you can just add them. That's for another day. So our error, epsilon I, is normally distributed with mean 0 and a variance, sigma squared. And what that means, if we sort of put that all together, it means that we've got our equation here that looks like this, looks now very similar, but it's basically the same thing, which is yi is a mean, so an expected value, plus and some error, which is a normally distributed error with mean 0, and that's the same variance term for all the yi's have exactly the same variance term, and they're centered around 0. And that's important because this is one of the assumptions of our model that we'll return to later when we have to check our residuals and check that the errors do conform to this assumption, because we are assuming it as part of the linear modeling process. This is useful as well later on in a course or a module, because you'll start to see that as we build ever more complex linear models, all that will change is essentially you'll have an error term off over here. All that will change is we'll have is this fixed part will get bigger and more complex, and there might be a transformation function in here on that fixed part as well, or even on the whole thing. So that just sets us up though for later. We can write this out differently again, actually, and this is sort of, I suppose, a more statistical way of thinking about it. So this here says that yi, our response variable, our data, yi comes from a normal distribution. That's what the tilde is. So yi comes from a normal distribution with some expected value based on parameters, based on other explanatory variables in here, and some leftover residual variance that we can't explain fully with just the fixed part here. So if you want, this is the random part here, so this is the noisy random part here, and this here is the fixed part, and that's, again, I suppose this is entirely equivalent to this equation of here. This is a more algebraic way of thinking about linear regression, if you like. This is a more sort of statistically sort of variance-driven way of thinking about it. But actually, this will be a useful way to think about things when we get later on. So I'm just flagging it here because we will want to start thinking very clearly about whether we want to start thinking clearly about whether we're talking about the fixed part here, the expected value and explanatory variables, or whether we're thinking about the variance part over here. And later on, we'll start to be able to break that variance up as well and start to do some more complicated modeling here with the random part of the equation. So that's sort of the basics of it. We can move on to some R code. Now, there's lots of books out there you can read about linear modeling and go through the maths and go through the underlying theory behind it as well, but that's as far as I'm going to go. So we can start getting on here. Again, some housekeeping, remove everything in the memory. I'd recommend instead, or at least at the beginning, start a new session. I've done that here. I've just loaded up a new session. We're going to work with a data set here called grazing.csv. This comes from a slightly modified version that I've taken. It's a data set that's used in chapter 10 of Michael Crawley's 2008 book. Actually, there's a newer version of that out now, I think, called Statistics and Introduction Using R. I use this book a lot in my courses, and I recommend that. It's a really good book. I agree with about 95% of it. Where I disagree, I'll cover it in these tutorials. So we're going to work with this data set here. So it's worthwhile reading that in again and just having a look at. And that's not working because I need to change my working directory for this. So I will do that. Set my working directory to the source file. Right, so there we go. So we've read in the data into an object called seed data. We'll look at the first few rows of that there. So we can see we've got two columns, root and seed. This is the amount of seed produced by plants in grams. This is the root diameter of the plant, the size of the plant basically, at the start of the experiment that was done. That's going to be in possibly centimeters, I guess, 6 centimeter root diameter. Seems quite big. I don't know. Could be millimeters either. I have no idea. Anyway, so we've got seed and root. So seed is our response variable. Root is going to be our explanatory variable. We can look at the structure of those just to check. So we've got a data frame object with 40 observations, 2 variables. Both of them are numeric, so that just makes our life nice and easy. That's exactly what we want to do. So we want to regress or plot one against the other. So a quick plot, we're going to plot this as, we're going to plot this here using the formula notations. We're going to plot C, that's our response variable I said, by root. So we'll just take a quick look at that. This is what our data look like. The amount of seed produced here in grams, root diameter, I've written centimeters. I'm actually not sure that's entirely true, but anyway, we'll leave it for now. And we've got this straight line relationship here that we want to try and estimate and fit with a regression line. So, because if we start plotting with that formula notation, if we start plotting in base R at least with this formula notation of seed by root, with the data is specified as being held in a data frame called seed data, then it makes our modeling very similar. So essentially what I can do is realistically just copy that and paste that in down here, so which I've pretty much done. So I'm going to write a model one. So we're going to run a linear model with the function. I'm actually going to use GLM, not LM. So we're going to run a model here with GLM. GLM is general linear model. There is a linear model function called LM. I think it's probably better off just getting into the habit of using GLM, which is more, as you can might imagine, more general and more generalizable. It allows a lot more options that we use later on in the course. So why not just use GLM all the time when we do it? So we do a GLM of seed by root, just like here, and that way we don't make a mistake. We know that whatever we plotted, we're going to model it in exactly the same way, where the data is held in the object seed data. We're going to save that output of that. The output of that call there is going to be saved into this object called model one. It's your choice what you call it. You can call it whatever you like, but I tend to call them, I actually tend to shorten that and tend to call them M1, M2, M3, M4, and that's just what I do. Other people call it mod 1, mod 2, you might call it model 1, you might call it my seed model 1, or whatever. It's absolutely up to you. We're going to store it into model 1 though, and then we can take a look at what model 1 is. So model 1 is not got a huge amount of information in it. It tells us what the call was that created it, and it was the copy of the formula we specified is GLM. Again, a formula is seed by root, data is seed data. It tells us what the estimated coefficients are. So it tells us here that the estimated intercept in our model, our beta naught, or our y-axial intercept, is minus 41.29. And it tells us that the estimated coefficient of the variable root, so that's the beta 1. If you go back up here, those are the beta naught here, because that's the intercept, and the beta 1 then is the coefficient. X here is root, y is seed, so the beta 1 is the coefficient of root, which is there, given to us as 14.02. And then it tells us a bit about the degrees of freedom. It tells us how many, what are the degrees of freedom of the model, so that 39 is the total, so it fits a null model in the background. The null model is effectively just the mean and the variance. There's no effective root in there at all, so that's what the null is, and that means that there's one parameter fitted, so that's 40 minus 1 is 39. That's how many data points we have, 40. And the residual error is the residual left over after fitting these two coefficients. So there's two coefficients there, so it's 40 minus 2 gives us 38 degrees of freedom. It tells us what the null deviance is. It tells us what the residual deviance is. We don't have to worry too much about what those are. Those are the sums of squares. And then it tells us, it gives us an AIC value that we'll come to later on. Generally, that's not sort of an output we'd look at. I'm just showing you that because that's what it is, and that's what's there. Normally, we'd use the summary option to get a slightly more rich output. So if we type summary model 1, we get much the same. So it'll tell us now again what the call was made to it here. It tells us more information on the deviance residuals. We'd expect those to be around about 0 in the middle of the range. It tells us what the max and min of the deviance residuals are. It gives us an idea how far away each of the biggest, how far away the data points are at most from the line, plus or minus, how far away they are on average. And you can see they're nice and symmetrical. So it's minus 30, plus 24-ish, minus 10 for the first quartile range, plus 11-ish for the third quartile range, and near and around 0 in the middle for the median, which is what we'd expect. Then tells us more information on the coefficients. So it tells us again the coefficients here, the coefficient of the intercept. So the intercept here is included. Its value is minus 41.28. The reason actually that's called a coefficient is, you might be wondering why it's a coefficient, because you'll see here in the equation it doesn't seem to multiply anything. But actually the B naught is actually multiplying a 1. So it's B naught brackets times 1. And we just don't ever bother really writing that out, but there is a 1 in there. So this is a coefficient of the intercept, which is included in the model by the model including a 1 value in here in the matrix when it goes to calculate it and run it internally. So beta naught is a coefficient. It's the coefficient of 1, so it's just sort of a special coefficient that we don't normally write about, song and a dance about too much. So the intercept is minus 41.286. The coefficient of root is, the slope is about 14, and now it gives us an idea of the errors associated with this. So it's not just got the slope is not just the slope. The coefficient of root is not just 14. It's 14 with some error, and the standard error here, which is related to standard deviation, so it's 14 plus or minus 1.463. That gives us some idea of how certain or uncertain the numbers are. That then is used to calculate, in conjunction with the sample size, is used to calculate a t-value. These t-values are then looked up in statistical tables, and those statistical tables tells us whether these estimates are significantly different from 0 or not. And if they're significantly different from 0 or not, it returns an associated p-value with the probability of observing. This is the probability if we observed a slope of 14 plus or minus 1.463, which we did do, what is the probability that we could get something like as extreme as that, or as big as that, or more extreme, if there was no effective root? So if we just come from the null model and there was no root in there at all, what would be the probability that we saw a value of 14 or bigger? And the probability of that is absolutely tiny, as you might imagine. This is a very far away from 0 estimate. The errors are small around it. It's 14 plus or minus 1.5. It's the kind of standard error estimate. And so we get a p-value here of this 1.1 e minus 11. That's 1.1 by 10 to the minus 11. So it's a very, very small number indeed. So it's highly significant. We observed a slope of 14. The chances of getting that from a null model are extremely low. And so we would say here we've got a significant relationship between the amount of seed produced and the size of the root diameter. These stars here, you get these significance codes. R by default sort of returns these significance codes. That tells us 3 stars tells us that the p-value is between 0 and 0.001. So ours is tiny, so it's way off down here towards 0. If you get 2 stars, it's between 0.01 and 0.01. If you get 1 star, it's below the biologically acceptable kind of magic number of 0.05, so that means it's significant. And you get a dot if it's just in between that, outside that, between 0.05 and 0.1. And you get a blank if it's anything bigger than 1. So I'm not going to get into the philosophical arguments about p-values here, but only to say that these are significance codes, if you like, and you get a p-value here that you can work with and write up. We then come down here, and it again tells us what the null deviance is. So it tells us what the null deviance is. It's a number on 39 degrees of freedom here, and the residual deviance is much, much smaller, and that's because our line actually explains a lot of the variation in the data. We get an AIC value, which I'll come back to again. The number of Fisher scoring iterations, I'm not going to go into it all here. We generally just don't worry about that at all. So we've got an equation fit to the data. I suppose the thing we'd like to do is then draw it onto the plot. Oh yeah, one thing I'll say here is about the r-squared value. So you'll see, so commonly people want to have an r-squared value, and the r-squared is related to how much of what proportion of the residual variance is, what proportion of the variance in the data in the null deviance is attributable to the model here. So we don't actually get that number out automatically from a call to summary of a GLM object, but you can kind of force it here. If you type summary LM model 1, you can then force it to give you what the basic linear model output is, and it'll give it to you if it can. If it can't calculate it, we'll see some of the more complex GLM models that can't calculate it, but if it can calculate it, it will. So it'll return here an estimate of the r-squared values. You'll see you get pretty much the same information as above, just slightly different information down the bottom. So it tells us what the residual standard error is. It tells us what the multiple r-squareds are then. So the one we really want to look at here is the adjusted r-squared. It's about 0.6996. So it's about 0.7. And that means that nearly 70% of the variation in the data can be explained by including the parameter root. By including a slope and a relationship between seed production and root, we can explain 70%, approximately 0.7 a proportion, which is 70% of the variation. So 70%, we go back up here, and on a null model would look like this. So basically our model, by including here in this equation, by allowing here in the mu, the expected part, by allowing root to appear in here, we can take away from that. The random part here shrinks, and we can explain 70% in the random variation part of the data can be explained by including root compared to a model that does not include root as an explanatory variable. So we can go on and continue with our plotting. So that's how we generate that. I'm actually going to do that here. I'm going to write the code in whilst I think about it. If we ran a GLM call, we can force so summary.lm model 1. So what you'll notice is these are called overflow methods. These are summary is a generic function. It will look at the object model 1 and it'll use whatever summary function is most appropriate to the class of object that's in here. So model 1 was generated with GLM, so it'll automatically call, and actually by calling summary, it'll call a function summary.glm, because it will try to match the class of object it'll seize with the function method that's contained in R for it. You can override that by calling .lm. So summary.lm will force the summary for LM objects to be calculated on a GLM object here, or whatever object is passed, and it will do it where possible, otherwise it'll throw an error. Okay, so that's how we can force it to do that in that case. So we go on and we plot the results of our model. We want to add a straight line to this graph here. What I'm going to do is here we're going to use the AB line function. So we're going to run the plot function again, so that just creates a nice blank plot there. And then it's really simple. When you've got a straight line, single straight line relationship like this, it's really easy. You just use the function AB line. So that adds a line using two parameters, A and B. Those are the intercept and the slope of a model. That's what the AB part is there. AB line. Look, and it'll just look inside model 1. It'll find the intercept, it'll find the slope itself, and then it'll plot a line on it, and you can specify the color red, you can specify the line type, the line width, etc. So we can just very quickly do that. That draws a straight line through the data points, and that's the best fit line that the model can find to explain those data. And even visually that looks pretty good. So that's all our model is. Now, what we want to have a think about is, we might have a think about what these numbers actually mean. We just do that kind of quickly. The intercept is minus 41. So that basically says that when x is 0, y is minus 41. So we're saying there when root diameter is 0 centimeters, which is off over here to the left somewhere, when root diameter is 0 centimeters, the expected amount of seed produced is minus 41.3 grams. So that's, that's what the number is, and it's a cautionary tale there in terms of not extrapolating your fitted model too far outside your observed data and thinking about what these numbers means. Sometimes the intercept is meaningful. In this context, it's not meaningful because you cannot have a plant of root diameter 0 centimeters. It can't exist. And on top of that, you certainly can't have minus grams of seed produced. So our model is fine. Our model doesn't mean our model is wrong or inappropriate in any way necessarily. What it just says is that our fitted model is appropriate probably only for the range of root diameters and seed production that we've got and observed in our data set. So we've only suitable for somewhere between a root diameter of about 4 and 10 approximately. And that results in positive amounts of seed produced. We don't have zeros and things like that screwing things up. So we just need to think about that. And then that's what the intercept means. It might be more meaningful, like I said, in some other examples. The coefficient of root, though, does mean something. So it's a value of 14. That means that for every 1 unit increase, it's a slope, so it's just like walking up or down a hill. For every 1 unit increase in the variable root, the y variable, which is seed, changes by plus 14. So if we look down on the graph here, if we go from 5 centimeter plant to a 6 centimeter diameter plant, the amount of seed produced will have gone up from here to here, and that amount it's gone up by is about 14 grams. So it's from here to here, it's gone up by 14, and exactly the same thing happens again. From 6 to 7, that's a 1 unit increase in root diameter, means it's gone up from here to It's gone from here up the slope to here, so that's gone up again by 14. And we know it's gone up because it's a positive number 14, and we can see it on the plot here. So that's exactly what that means. So it's entirely, you know, in terms of putting context onto our numbers and things we get out of these these models, they can be very informative, and generally you want to be able to put some context on what this slope means. So here it means a 1 unit increase in x corresponds to a 14 unit increase in the y variable. So that's what our model is, that's what our model looks like, but we need to check these model assumptions that we defined. Remember we talked about those equations up the top at the beginning of the tutorial. We need to have a think about whether they match them. And if you remember again, the assumptions were that the errors here, the epsilon i's, are normally distributed with mean of 0 and a common standard deviation. They've got or variance. So they've got a variance or standard deviation that's exactly the same for all of them. And key thing is that these errors here, this variance term is independent of, and it's separate to these estimates here. So it's separate to x. The variance here has got nothing to do with x. X is not part of calculating what the variance is. The variance is the leftover bit after accounting for x. That's what that is. So we need to do a couple of checks of the residuals. So the best thing to do is to extract the residuals into another object I've called it RSD. So the function residuals, or the shorthand resid, is the same thing. So we ask R to calculate the residuals or extract the residuals from the object model 1. I'm going to store that into something called RSD for now. So that's that. You can get a summary of those actually if you want. I didn't do that, but if you wanted to get a summary of those residuals, you'll see that again, just like it gave us in the table, the output table for the summary.lm and the summary.glm. It'll tell us what those are. So those are an indication of how the biggest residual is plus 20, nearly 24. The smallest one is about minus 29 units away from the line. That's going to be that one there, I guess. It's about 29 units away from that line, like that. And one of these two is about plus 24 units above the line. So then we want to have a look at those and make sure that they're normally distributed. So one way to check that they're normally distributed is to use a basic histogram. So I've calculated a histogram here of the residuals. So those look pretty normal, centered around 0. Got a sort of tails off to the side. You might want to add you might want to change how many of those boxes you plot, but it doesn't really make much of a difference. That's a histogram there, a normally distributed histogram of those residuals. Perhaps a better way to visualize that though, and check the assumptions of it being normal, is to use what's called a QQ plot. So QQ is quantile plot. So let's have a look at that. So we'll do a QQ norm is the function to generate that, QQ norm of RSD, and then I'm going to add on to that I'm using the function QQ line, a straight line, just to help me visualize it. So QQ norm of RSD gives us this kind of squiggly S snaky plot here of the data, and if we do a QQ line, we get a straight line through it. So this plot is what's called a normal quantile plot. It shows what the theoretical quantiles are. So if these things were perfectly and normally distributed, the data, these are the residuals. So if these residuals were perfectly normally distributed, they would fall along this axis here. These are the theoretical quantiles of where we'd expect them to be. This is the sample quantiles. This is where they actually fall on that spread from on that assumed normal distribution. And you can see that the red line shows us where they would be on a one-to-one. So this would be where they were if they were absolutely perfect. So you can see most of our data points fall under that normal distribution curve really quite well. One of them's a little bit way off down here. These ones start to snake away a little bit here as the values get bigger. Bit of an art form here is to decide when to get worried out about this kind of thing or when to not. You might want to think about doing something with that, but we'll actually see later on in one of the next tutorials that we can improve this model with it, because I've actually summarized that sort of I've left a key variable out of this analysis for now. There's actually another variable in there that we can allow for, and that'll improve this model fit. But for now, that's still really pretty good. So we've got a normal QQ plot that looks really quite good there, like that. We've got a histograms that look good, and we've got a basically straight. I mean, the bottom line is if you eyeball it, it looks like it's gone straight through the data points. A little bit of extra checking on your part like this, and can really reassure you that everything is fine. So the other thing we might want to do is plot and check for the other thing that we want to do. So we've got our residuals are centered around 0. That's what we want. They're also normally distributed, as good as. That's what we've got as well. The other thing we want to do though is check that, like I said up here a minute ago, that this error term here, these residuals here, which are these, have nothing to do with the expected value, what mu I, which means they've got nothing to do with the explanatory variable x. So what we want to do is just see that there isn't some obvious pattern in the data with x. So something you might do is plot the residuals here. So I'm going to plot the residuals against my explanatory variable root. So that's here we've got my residuals now plotted against the explanatory variable root, and we expect them here, the residuals, we expect them to be 0. So I'm going to add a 0 line on that. I'm going to add a 0 line with the AB line function. I'm going to tell it that the intercept is 0, the slope is 0, and use the color blue to show it. So let's put a blue horizontal line here. So we expect our values to be centered around 0, which they are. We also expect there to be no now obvious pattern with root. We don't want, because these residuals are independent of, assumed to be independent of the explanatory variables, all of them, including root, we expect there to be no relationship. And I suppose the point here is that there maybe is some relationship. These values here almost look like they're going, you know, it looks to be almost like there's a trend there and that there's another trend there. So if you think about it, as we look along root here, the residuals start off negative, they get bigger, and then they fall back down to be negative again, and then they get bigger again. So that might lead you to some cause for concern that there actually is some sort of pattern here, that the residuals are somehow dependent on the x variable root. That in general sense would be a problem. In this case it's not, because as I said, there's another variable that I've omitted from this very basic analysis. So this, we're just going to sort of flag this and park it, and we'll pick it up in another module later on when we look at fitting 2 lines to the data. There's actually 2 lines through these data, and that's one of them. That's one of them there that we see, and that's another one there that we see as well. Don't know why that keeps doing that. So if we look at these plots together, just very quickly, make a panel plot. We're going to look at the raw data on the left side. We're going to look at these residuals on the right side just so we can see what's going on. So this is what's going on here. So these are our 2 plots side by side. So what's going on here is these data, these residuals here are actually this here, and there's actually one line. There's one line here through the data, and these other residuals are here, which are these ones here. So there's actually 2 lines in these data. And that's what we'll come on and look at and explore in one of the next podcasts. So that's that. You can save your data if you want. Again, I don't do that usually, so I just leave that there if you really want. But I don't do that at all. And then there's an assignment here. So if you look, there's a little assignment for you to work on. If you look at the HTML, if you get access to the raw files here, you'll be able to follow along in the solution down below there. So yeah, we'll pick this up again. Actually, I'm going to record another podcast very quickly that shows us how to add lines using a slightly different method. Not the AB line is fine when it's really simple, but we need to use a function called predict later on in the module. So I'm going to run through that quickly on this simple example in a separate podcast now in a few minutes. And then we'll pick this up again afterwards when we start fitting more than one line on a page and start being able to compare those statistically.